Okay, we can start by the first keynote talk by Michèle Sebag, Research Director of CNRS.
Thank you. So I'm very pleased to be here and to say hello to my German and French friends. It's a pleasure. I will present work done at Université Paris-Saclay and in Dataia, which is one of the French institutes in AI, which is about learning to learn. And you know, I will start with some examples of the irresistible AI ML wave. I'm aware that this is not the kind of examples that you might have chosen. So just think of your preferred achievements in AI. So it could be in computer vision, could be in games, could be in natural language processing. All this is very impressive. And now the question is that, you know, there is also a black side, right, in AI. And then there is the fact that we are facing a shock because with respect to prediction, sometimes we have troubles. With respect to decision, I think that many of you spoke about the biases. We can make a dystopia from the world led by AI. And there is also, and if you want to use AI-guided models to make interventions, then it can become really a problem. So what we would like is an AI with common decency, fair, accountable, transparent, robust. But I will not speak about this today. I will speak about the fact that, as Katharina said, the AI doesn't mean GAFAM. And we should not think that the achievements, of course, everybody is impressed, and I am, by Google and Microsoft and all the others, is the only thing there is to see in AI. And particularly, we have two concerns. One is the cost in terms of computational power and also in terms of, you know, the amount of data, because typically, I will come back to this, in industry, there is often the case that we are dealing with very short, small amounts of data, and there are many things to be done here. And what we would like today, this will be the focus in an affordable AI. So we all know that, you know, running the model is just one instant of the AI project. And before that, you have to prepare the data, to clean the data, and all those very modest and humble tasks, they consume a lot of time and the major part of the AI application, right? And this is known for decades. So what we need, okay, I apologize because you as everybody is aware, I'm an expert doesn't mean wearing a tie, but the point is that in order to enable machine learning and AI, we need computational power and expertise, okay? And the shortage of data scientists is one of the main trouble in our field. So at least in order to, to disseminate the progress of AI in the industry and also in the labs of science in other disciplines. So I will try to define the position of the problem, how to make an affordable AI or model, building models. So you see, we have the fact this is what any software editor would like to see, right? Just press the button and it all will be done. And what you have instead of that is a very complex little board, okay, with many buttons and you know. And the question is that, of course, if you are in a research lab, kind of, you call a PhD student and you say, make it work. But if you are in another part, then life can be a nightmare. And we are not at the time where making it work for a specific application was worth a PhD, right? We must kind of become professional in deploying AI. So, in many domains, actually, not only machine learning, but many others, typically constraint satisfaction and stochastic optimization and the like, right? What you have is that you face the no free lunch theorem, right? That is, if there is no killer algorithm, which means that people the scientists, will tend to build algorithm portfolios, right, with many options, right? And now it becomes a full-time game to select for your favorite application what is the best algorithm and how to tune it, right? So this is the algorithm selection, meaning selecting the algorithm and selecting the best algorithm configuration, selecting the best hyperparameters. This becomes a key bottleneck in the ML and AI deployment, right? You can want to do this for your particular, say, distribution of problems or this key problems, but the problem is the same, right? So you face this problem in all those domains, right? And as I said, we have to solve this key issue, the algorithm selection and configuration, in order to be able to deploy this outside of the computer science research lab. Okay. And I think that this issue was acknowledged in the end of the 80s, right? There was also this European project which was called meta-learning, okay, already at in the previous century. So this problem, what is the good brand of machine learning for your particular problem, could actually be formulated as yet another learning problem, right? You could say, okay, assume that I have something which is a kind of distribution of problems instances, right? Assume that I have something in order to, which can describe my problem, and this will be the topic for this talk, okay? Assume that I know that the criteria I would like to optimize, and then I am able now, at least this is the title of the game, I would like to know how to select the good features, the good hyperparameters, and the good algorithm, right? This is the AutoML problem. And you see, there has been a number of international challenges in this. Isabelle Guillon was one of the leaders of the field. And this was also in all fields I mentioned, which are all related with combinatorial optimization, constraint programming, constraint satisfaction, algorithm selection, okay? Why is it so difficult? Because you have a black box optimization. You don't know, you don't have an analytic description of the function that you want to optimize, which means that when you want to see, okay, now I'm trying this configuration, what's the result? You have to compute. And this is very expensive, okay? So this is interesting to see that actually the problem is presently much better solved in the context of constraint satisfaction and constraint programming than in the domain of machine learning. Okay, so this is basically what the different approaches to this AutoML problem. Basically, you can have something, okay, I'm trying to see if I can use this, you can tackle this as an optimization problem, that is, you try to focus on the most promising, say, algorithm configuration, or you can try to do this meta-learning, and as you can see, I will focus on this, right? So I will not speak about deep learning, which is a problem per se. I will speak about the ordinary tabular data, which is still, besides the hype, which is still something which is more than, I would say, a majority of problems today, right? Okay, so this is what we want to do, AutoML for tabular data, and we would like to say to be less expensive as possible, right? So, considering that AutoML is yet another problem, you need examples. That's as usual. You need examples. You need to know how to describe your examples. And now these examples are at the higher level. That is, one example for the meta-learning is one data set, okay? And then you would like to construct your benchmark, and then you will learn a model, how will this particular algorithm will behave on this kind of data set. And now, this is the last simple step. You select the expected best one. That's simple. Now let's see how we can make it work, right? So, okay, we need to have examples, as in machine learning in general. At the moment, what we have is benchmarks, and they are very small, okay? Like, okay, that's terrible. It's like only thousands of examples. That's not enough. But the real bottleneck is about the features. That is how to describe a data set. I will call them meta features. So what we have has been developed for 3 decades now. And you see okay, you have examples there. And you see that they are kind of shallow. The most informative are those landmark things, right? Okay, here, which is actually, you describe your data set by the performance of an inexpensive machine learning algorithm, and that way you can capture something of the difficulty of your problem. But this is expensive. So the problem is that the meta features we have at the moment, they have to capture a distribution. They have to be inexpensive, because if you spend a lot of time in describing your data set, then typically it's better to try and run. And you want those meta features, to be sufficiently expressive to capture the fact whether 2 data sets are actually similar with respect to the algorithm. That's the point. And now I will tell you how we can do this, how we can leverage machine learning in order to learn those meta features. So assume that you have a machine learning algorithm or pipeline. Could be a support vector machine, could be random forest, could be auto-scalar, right? You have the configuration space, can be a dozen for 100 dimensions. And you have a set of benchmark problems. As I said, we never have enough of this. And then you have their basic representation, that is their description as a vector of the computable meta features. This is the for free kind of description of a data set. Okay, doesn't tell much. But now, for some of those benchmark problems, you have the solution. That is, because people have tried this. I should have cited the OpenML repository, because people have been trying lots and lots of configuration. So for those data sets, you know what is the target representation. That is actually the set of configurations that do well on your data set, right? And I will call them the target representation. If we had this target representation, we would be done, okay? But we only have them, as usual, when they have been kind of labeled, when they have been tried and considered by the whole community. So what we want now is we would like to find a good metric on the set of data sets, such that if I tell you, you have this data set, right? You see the nearest neighbor of your problem is this known problem. So you can just keep the good configuration for your nearest neighbor problem, and you apply them on your problem, right? That's kind of nearest neighbor approach, but at the meta level. Okay. And then, okay. The uncrafted meta features do not reflect the target matrix. You can guess this, because if it was not the case, then the problem would be solved, right? So you see here in this case, you have 3 data sets, and you can see that the nearest neighbor of the blue, when I'm looking at the initial meta features, is the green. And when I'm looking at the target representation, is the orange. And when you plot this, you can see that this apparently nearest neighbor, the green, does not do well, does not behave well, does not deliver good recommendation when I'm in the configuration space. Okay, that's the idea, and that's what we want to change. So what we'll do is this, actually, 4 steps, right? we take a benchmark, we take their target representation. You can think of them as labels, right, if we were in supervised learning. Now we find an intermediate representation, that is a kind of representation that mimics the metric of your target representation. And this I will call the intermediate representation, right? And I will come back to how to adjust their dimension in the end of the talk. And then we just want to map what we have, that is the initial meta features, on what we want, that is this intermediate representation. And what we'll be using is optimal transport. So I will, okay, and I know that there are many specialists of optimal transport in the room, so they will help me in answering questions. And then this is just one crash, say, remind of optimal transport. So you can see that this is actually a very old domain, right? It was in the, before, I think, in French Revolution, and you have Gaspard Monge. And you see here the problem is that, this is the continuous problem, you want to see how to efficiently move all the sand, which is here, the heaps of sand, you want to move this into the hole here. And you want to do this, so you have one distribution, this is mu, and you want to map this distribution on this distribution mu, and in such a way that you minimize overall the transport cost. Okay? So this is the so this is the continuous version, and you have the discrete version. So it was the war, and then the Second World War, and then Kantorovich was trying to see how to send the soldiers from where they were, okay, to the cities and the boundaries. So I will come back in the end also to this issue of war. So formally, what you get is the following. You have two distributions. You have your initial distribution mu, your target distribution mu, could be discrete distributions, as they are in the Kantorovich case. You have something which is a transport cost. And what you'd like to see is how to map your mu onto your nu, right, in such a way that it minimizes the expectation of the transport cost. Right? That's the way. Say this was one slide. Actually, it was a bit too much to put all this in just one slide, so there is a second slide. And you see here, actually, you have two ways to transport the things. And one is, I would like to transport things in such a way that I minimize the transport. That's one. But in some cases, I would like to do the transport in a rigid way. That is, I want here, you see, not only to map x on x prime in such a way that it works here, but I would like to map x on x prime in such a way that, no, sorry, I would like to map x on y and x prime on y prime in such a way that the distance between their image is about the same as the distance between the 2 points, right? As if you take just the pile of points and you transport them onto the other pile of points in the best possible, right? And you will see that we need actually both in what we will be doing for, I'm coming back to AutoML in just one second. So this is the Wasserstein loss, you preserve the distance, and this is the Gromov-Wasserstein loss when you want to have this rigid transport. Okay. Done with optimal transport, and then now let's apply this. So we've tried to summarize all the story of the AutoML approach that we are proposing in just this figure, okay? So here you have the target representation, right? For each data set, you have the distribution of the group configurations for these guys. And now you can map them into something which is vectors, okay? Because it's easier to deal with vectors than say distributions on the data set. Okay? And now this is what we have at the beginning. This is the initial description. And now what we're trying to see is that this is the target metric. this by construction preserves the target metric, but we don't know this for new data. So what we try is to find this. That is, this is an image of what we know, the initial representation, in such a way that it has it offers the same metric as U. Okay, so that way here we have the best of both worlds. We have something which can be computable and which contains and which contains the information of the benchmark, right? So what we do is this: we are trying to find the mapping from the initial representation to something, such that it will minimize the fused Gromov-Wasserstein distance. You see that there is here there is a trade-off between the transport and the rigid transport, plus something which is just a regularization term. And what we get at the end, you get a new representation, which is a function of the initial representation. So now you know this. Now you can do this, which has a similar metric as your target representation, which is where the meaning is, where the information is. Good. So that's the way it works. And now let's see how are the results. So if you allow me, I might be a bit short on the experimental validation because, you know, basically the message is that it works, right? And then there is a table full of figures, and then you see that it works. Okay, so let's see. So we compare with the baselines, of course. And the baselines might be the initial meta features, could be also the auto-escalern meta features. And I forgot to say that actually auto-escalern is a real hard competitor because this is the winner. This is the Frank-Hutter and the Matthias Ferrer and the other works. And this is the winner of all the AutoML challenge worldwide. Okay. And you have others. You have also the landmarks. That is, you see, you describe here, you remember. Landmarks is that you describe a data set by how well, say, a set of algorithms do on this data set, right? And we're trying to see whether we can do something good for, say, algorithms, the main algorithm, ADABUS, random forest, support vector machine, and also a pipeline, which is auto-escalern. And the figures here, between parentheses, is the side of their configuration space. So you can see that actually for the pipeline auto-escalern, you have quite a number of, the dimension of your pipeline is high. And there is no hope that you can tune and get them the good point just by hand, right? And you have the benchmark, which is the OpenML CC, by using a leave one out validation. The first task is to see whether METABU, meta features for tabular data, captures the target metric. So the performance indicator is the normalized discounted cumulative gain. You see, this is exactly the same kind of indicator that when you want to do information retrieval, that is, you compare what you get with what you know you should get. And basically, you see from this, the higher is the better. The index here is the K for NDCG at K. And you can see that, in short, it works, and it works better than the others. That was the message. So this kind of figure is for the specialist, but then I hope that it's not too boring for the others. So the other one is that the second task is that you use your METABU in order to sample your configuration, right? So you sample again and again, and you see what is the best result, performance, that you get in that number of trials. And you see, because figures, performance figures, they don't see much. You see how many times you win. That is, your metric, your performance indicator here is the rank, the average rank over the 80 data sets. And you can see again, this is true for random forest, this is true for ADABUS, this is even more true for SVM. But then this sampler of configuration actually get good results. Now you see, it's not because you have a good sampler that when you put this into an optimization engine, that you will get good results, right? You have the initialization, but then there is the search. And typically, if you want to have good results with the search, your initial point should be sufficiently diverse so that you are sure not to let, say, spots unexplored. So now what we do is that we do the initialization of the auto-escaler itself, and we don't touch anything but the initialization, okay? And you see whether you can improve. Okay, so the blue again is METABU. The orange here on the left, this is auto-escaler, and here this is just to give you a comparison. This is the best out of I think it's 8 random trials. So this is the auto-escaler, and this is another one, which is probabilistic matrix factorization. And you see, when you put your features, the METABU features, within the auto-escaler or the PMF, well, actually, you improve the overall results. Good. This is the time, right? So you can see that this is the time. You can see that actually it's modest, right? So I will come back to this if there are questions. And then I'd like to see, in summary, what did we learn? Because, you know, the title was a bit ambitious, learning to learn. So what did we learn actually? So the first thing is that, okay, so this is what we get. We saw that meta-learning, those meta-features, could learn new meta-features that could capture the topology of the good topology, right, the target topology, and it behaves well compared to the state of the art. So this is what you can expect when it works, right? And the code is available on the GitHub, right? So it works. That's the first message. The second message is something which is more interesting. So we have this problem, learning, and now our points are data set. So what is the dimension of the space we are dealing with? You might remember that in the old days of data mining, okay, people were considering, say, difficult problem in astronomy, and they were seeing that there are some problems that would escape say, the human scientist, although their dimension was something like, say, a few dozens. Right? So what exactly is the dimension of this machine learning problem? And C, okay, and we have a way to compute the intrinsic dimensionality of this. So basically, the idea is that you see, when you are in dimension D, when you assume a uniform distribution, so that's unrealistic, but you see the idea, then the number of points in the ball, okay, grows like the radius of the ball to the dimension D, if D is the intrinsic dimension. This is the idea. And when we apply this, you see that actually the dimension of theta, the configuration space, has nothing to do with the intrinsic dimensionality of the AutoML problem. What's just unbelievable is that you see in AutoScaler you have 100 parameters. Just because you have the parameters of FCVM, you have the parameters of all the algorithms that are within the AutoScaler umbrella. And then actually you see that your intrinsic dimensionality is low. So we had a kind of discussion with the reviewers. Okay, it was back and forth, because we were saying at the beginning, okay, when the dimension is small, it means that the problem is simpler. And then the reviewer was saying, come on. You have the fact that AutoScaler is a superset of SVM. Okay, and it looks, from what you say, it looks simpler to solve the problem with AutoScaler than it is for SVM, which is a subset of this. So we had to discuss a very long way, so it was at the I cleared this year as a spotlight. And to my knowledge, this is the first time that we have something, at least a guess, about what is the dimension of the problems we are spending our lives on. Okay. another point, which to me is even more important, is the fact that we can start to understand something about what makes a problem difficult, right? Because you see, it's kind of a black box. That's a problem already. But now we can, okay, so this is what you see. Okay, so you remember we have the learned representation, the METABU representation. So this is a projection in 2D. We have here for each of the initial meta features. So for instance, the percentage of missing values. And we see here how important it is, typically for ADA boost, if I'm right, yes, for ADA boost here in the second coordinate, and for a random forest on the x coordinate. And you can see that here. So here again, we are just confirming the say the tricks of the trade, right? The fact that all practitioners know that the percentage of missing values is something which is very important for instance, ADA boost, and much less so for all decision trees and random forest thing. And now the question is now that we have the evidence, what makes a problem difficult for a given algorithm, then at least we have the basic tools in order to understand what's going on. We have the way to perceive and then possibly to understand better. So this is the idea. So now we have something which is what makes a problem difficult for a given algorithm. So from here, where do we want to go? You see, this representation is just for one algorithm or pipeline. What we want is to have something comprehensive and also compare the representation for the different algorithms. And you see, if we can really trust these new meta features, then we can do transfer learning and domain adaptation in a professional way. We will know before trying that those two data sets, they are related, and we can hope that there will be a good transfer from this to that. So that will be good news. And also, perhaps, we might say, moralize the way we assess the machine learning algorithms today, because we heavily depend on benchmarks, and it might be that we overfit benchmarks. So that's a worry, right? So I will end with thanking my co-authors. So Eri Rakoto-Harrison was going to Franco-German lab as postdoc, Isabelle Guyon, who say paved the field of AutoML, and Marc Chenouer, of course. And now this is not a slide just because I forgot, but I would just like to join the manifesto against the AI-guided weapons. We spend a lot of time speaking of ethics, and I think this will be a practical case, right? Thank you.
Thank you very much, Michèle, for your talk. We have time for questions. 5 minutes. Who wants to start the first question?
Thank you very much. So I think this is a great talk. So I liked it a lot, and I think this will very likely help a lot in the future. I would like to ask you have so far dealt with tabular data. So what if all the graph stuff and things like that would come into the game? So could this be extended? Would there be different technologies if you have graph structures, sequences as inputs, or would that need a completely different approach? So can you comment on that, please?
Thank you. Thank you for the question. I don't have the answer. So I would start by considering say the eigenvalues of the matrix of the graph. That would be a start. But you see, typically, I think that this is the point where it might be very profitable to bridge the gap with our colleagues from the graph and the algorithm, because you see, typically, also in the random-based networks, you can see that you can construct, for instance, an eco-state network based on stochastic features. And now, from this stochastic, some works very well, and others don't. So now we would like to need exactly the features that make the difference and that make some structure of graph so much. And actually, the graph NN is kind of trying to do this, but manually.
Okay, so let's thank again Michèle. Thank you.